I'll say.
Because, yeah, she didn't do it at GCSE. Okay, so big picture. We often have to find a root of a function, which is where it crosses the x-axis. And you can narrow down the location of a root to between 2 points.
Hmm.
So basically, if the y-coordinate changes from being negative to positive, or from positive to negative, then you can say there's a root somewhere in between.
Hmm.
Because y must have been 0 if the sign changed from negative to positive or positive to negative. And the interval means the x coordinates. So if one x coordinate is 1 and the other x coordinate is 3, then the interval is 1 to 3.
Okay.
What else? We'll get there. There are certain exceptions. This one, the sign changes. So here it's negative. Here y coordinate is positive. Is there a root in between?
No,
Why not?
because these are kind of like exponentials. They tend towards the line, but they don't touch it.
Yes, so basically it occurred when we divided by 0 here in the middle.
Hmm.
And this is called a discontinuity. So that's fancy for broken line. This is a continuous line. It's unbroken. This line is discontinuous, broken in the middle there.
Okay.
What value of x would cause the discontinuity for this one?
Um, 3.
Nope. It would be the x value that would cause us to divide by 0.
0. 1. 1.
Yes. So the equation of the asymptote for this one then would be x equals 1. What's that? Let's see. Fine. Sometimes you have a mixture of both. So some equations have roots and discontinuities. So this one here, I can see a root there. I can see a second root. I can see a third root. And then here you have it going from negative to positive with a discontinuity in the middle.
Hmm.
So this bit here, and I suppose some of the other stuff, is creating our roots, but then this fraction is creating the discontinuity. And so whenever you have an algebraic fraction with x on the denominator, then you might get a discontinuity. If there is no fraction, if there's no x in the denominator, then it will just be continuous all the way through. It's only
Continuous meaning.
unbroken.
Okay.
So it's only like if you have a function like x cubed minus 7x squared, blah, blah, blah. Now let's just say plus x minus 4. That's going to be continuous all the way through.
Yeah.
It's only when you have something over like 1 over 7x minus 3 here, you have the potential to divide by 0.
Yeah.
Whereas if there's no fraction, it's never going to happen.
Got it.
Okay. How about this?
1 plus if 1 is positive, is there a root? Potentially.
Correct. Potentially. And when would there not be a root?
If it's 1 over an x value.
Yeah. If the function is continuous, there's definitely a root. If the function is not continuous, especially in that interval, there might not be a root. How about this one?
Positive and positive. No. No.
Let's take a look. So the one on the left, no roots. The one on the right, there's 2 roots. So the
I was
interval.
thinking of that. Yeah.
So the interval was a bit too big, and so yeah, we can't be certain.
Mm.
Sometimes you get more than one root. So here
Yeah.
you have like a sign. There's no sign change, but there's 2 roots, or something like there's a sign change, but there's actually 3 roots type of thing.
Sure.
And then here you have 1 root with no sign change. So lots of exceptions. And then here you have discontinuity. When locating roots, drawing a sketch may help. However, if the sign changes and the function is continuous in the interval, then therefore there must definitely be a root. So that's the big thing. If the sign changes and the function's continuous in that interval, then there must be a root.
What's it mean by in the interval?
In between those two x values.
So technically 1 over x could be continuous between, say, 3 and 4.
Yes.
Is that what it's saying?
Yeah, so this one, you can see how the function is continuous, let's say, between when x is 1 or less. The function is continuous, but then it's like discontinuous when x is 2. So so in the interval of, let's say, 0 to, let's say, what's that, 1 to, let's say, well, that's a bit too, let's say 0 to -1. Yeah, 0 to -1, the function is continuous. It's unbroken. But let's say 1 to 3, it's discontinuous. Yeah. And so that's not a big deal though. Let's see. They sometimes write intervals like this. So this one looks like a coordinate, but it's actually just not or equal to. If they use square brackets for the interval, that means those two numbers are included.
Okay, I'll make a note of that.
And they don't use it too often. But
Okay.
let's see.
What do the little marks, if you go back, the little kind of these marks on the left?
Maybe that's old man language. It just means the same as the above.
Oh, okay.
So the interval. So this one, show that there is a root. I get the feeling that this is wrong. How could you show that there's a root in this interval?
So show that there's a root in the given interval. You make it equal to 0.
Nope.
Would you just... Oh, in the interval 1 to 2, so then you put 1 in, then you put 2 in and see if the sign changes?
Yes. Now I think that this is wrong.
Huh.
But let's just see. So in theory, okay, so for this one, the f of 1 is a positive number. The f of 2 is a negative number. Three things you have to say. The sign changes, the function is continuous, therefore there is a root.
The sign changes, function is continuous in the interval. Definitely. Okay.
And okay. And so you're pretty good for that. So try this one. And hopefully this one is correct.
9 plus 4. So 15 for F1, F2.
Okay.
Oh wait, no. 1 for the first one. And then minus 33 for the second.
Okay. So the f of 1 is equal to 1. F of 2 is equal to minus 33. And so it's a show that question.
Show that there is a root. So then we say the 3 points, so sign changes, function is continuous in the interval, therefore is a root.
Yep. That was minus 33 is less than 0. And that's formatted a bit weird for some reason. Let's see. Yes, the sign of the f of x changes. The function is continuous, therefore there's a root.
It's 1, not minus 1, I think.
Yes, that would negate the whole thing, wouldn't it?
Yeah.
Let's see. So, this is what these look like. They're alright. This is what exam questions look like. Is there any there that is worth doing?
We could just do the first one, or the last one, the hardest one. Which one's the hardest one?
In theory, it should be the last one because it's a 3 marker.
Mm-hmm.
No, it's a 3 marker instead of a 2 marker. Seems like
Okay.
it's the same
Well,
as
then
the
we'll do.
other one.
Okay, then we'll do the last one.
Yeah.
F of x equals x to the 4 minus 4x minus 8. Show if there is root in interval minus 2 minus 1. And those brackets mean that it's including minus 2 minus 1, or what does it mean?
That's right. Yeah.
Does it? It doesn't have any significance in this context, does it?
No, I don't believe so.
Okay. 2
It
minus
could
1.
potentially, but no, I don't think it will.
Okay. So for the first one, I get 16.
Okay.
So yeah, so f of minus, well, the x minus 2, 16, and then the second one is minus 3.
Okay.
So the sign changes,
Mm-hmm.
and the function is continuous in the interval.
Mm-hmm.
Therefore, there is a root.
I think that's it. I think that's full marks. I think this was worth an extra mark just because those square brackets thing. This one was written in a more kind of understandable way. Same with this one. And then the first one, very understandable.
Okay.
Let's see, this one. F of minus 2. Change of sign and continuity, therefore root in interval. Follow through the calculation as long as there is a sign. So, okay, great. Any questions with that stuff? How do you feel there?
Yeah, no, I get that.
Okay. This one, make x the subject.
Okay, so 0 equals x cubed over 12 x plus 1. So 1 or 12 equals x cubed minus x. Minus 12. Minus 12.
Yeah. So you're trying to make
Just
x equals.
Just x. Okay. So then you do just x equals x cubed over 12 plus 1.
So that's the simplest way. Plus 1. How would you make x cubed on one side by itself?
So then it is minus 12 plus, or x minus 12 equals x cubed.
Yes. So that will be. No. Hang on. We want
You
to
bring. Let me do this again. So you bring over the minus x and the
1.
multiply it by 12. So 12x minus 12.
I see what you're saying. Sorry. Yeah. I was thinking of it as a bracket. Okay. So
Oh.
12x minus 12.
Equals x cubed.
How could you make it x squared instead of x cubed?
You divide by x on the left hand side as well.
That would work. And so what would this become?
So it'll become 12 minus 12 over x equals x squared.
That'll do. And so that's what we get. Now make all three x equals. So how can you make the bottom two x equals?
Then you rearrange to get x on the left. So
there's a very direct way. Let's say the bottom one.
the bottom one, to get x equals,
How would you turn this into x?
divide by x.
I'm gonna do square root.
Square root. Oh, okay.
How about this one?
So then that one would just be cube root.
Yes. So this is just me trying to come up with some way to communicate it. Their questions are more explicit for that reason. So these are the three ways that you can make x the subject. So this was a cubic equation, and so there are three different ways you can make x the subject. there was x squared and x cubed, and then you end up with one being, x, the other being a square root, and the other being a cube root. Graphical simultaneous equations, you have y equals something else, and so you can bring the two together. You can just as easily bring them back apart again. So you can say y equals x and y equals the other side. And so this is what it would look like. This is the line y equals x. This is the line of y equals the right side.
This is the part that I just don't understand. So why can you do this?
So, well, imagine I gave you two simultaneous equations, and I said one is y equals x, the other is y equals x cubed minus x squared. And I would say, how do you solve these simultaneous equations?
You'd equate them to each other.
Yes. So you'd basically just say that goes there.
Yeah.
And so you could write that as x equals x squared. What you could also do, however, if you really wanted to, like with partial fractions, you can like unadd two fractions. You can also split them back up again. And so you can say y equals this and y equals that. Oops. See what I mean? And it goes back to being the original. Y equals x and y equals the other function. And so you can just the way that you can bring them together, you can also bring them apart. So here we have x equals this thing. So like we can say that this one's equal to y, this one's equal to y, and then just sketch them, or I suppose in this case draw them exactly.
Yeah.
How many solutions will there be?
So in this one there are 3.
Yes, and what that shows us is that this equation up here has 3 solutions.
So would that be if we bring x to the right hand side again?
Yes, that's one way. Another way is a numerical method, and that's what we'll look at.
Okay.
We zoom into this point of intersection. Sure. Yes. So there's a method you can do called staircase and cobweb.
Yeah.
Let's see. So I'll use black. So if we start with the initial value of 2, what we can do is we can say we're going to go up, we're going to hit the curve, and every time we hit the curve, we will go across and hit the line.
Okay.
So we have a little robot that does that for us, and it keeps when it hits one line, it changes and tries to hit the other. So our little robot does that for us over and over again. And what's it getting closer and closer to? Can you see what it's converging on?
Yeah, it converges on the point of intersection.
Yes. And it can say, like, read off what is that point of intersection. And it might say that's 1.1 because it's in between 1 and 1.2. So maybe it's 1.15 or something, 1.14, something like that. So we won't get like a nice exact answer like the cube root of something, but we'll get an estimate of what it is. Yes, that's called a staircase diagram. Okay, so now let us use the calculator to do what we just did. Well, should I? Recurrence relation. Okay. Do you know how to convert this into a recurrence relation?
Where you keep on clicking the equals button?
So to first write this as an iterative formula, recurrence relation.
Is it already in the form? You just do xm plus 1 and xm?
Yeah. So the x on the left side, the subject one, that becomes xn plus 1. And then all the x's on the other side become xn.
Yeah.
That's it. Yes. And now, okay, we could. Yes, now let's sub in. We want to find so x0 is 2. How can we find x1, x2, x3?
So for the x1, you just sub in 2 for xn,
Okay. So try
and then okay. So what you do is you type in 2, and then that saves it as answer. Then you go answer cubed over 12 plus 1, and then you just keep on pressing it. So the first one is 5 thirds.
Great. 5 thirds, etc. So you already know that method.
I have a question about this because I was doing some practice earlier today.
Yeah.
So obviously, if we go back just one slide, so here we're given, go forward.
This one?
Yeah, okay, here we're given x0, right?
Yeah.
Which we think is an approximation of the root, right?
Yeah.
However, why is it that when we use other values of x, say it's between 2 and 3, 2 could tend to the root, but 3 would just become a math error?
Hold on a sec. So this is one staircase. So if we use this x0, that creates a staircase. So just want to see something here. If I was to extend that a bit. What if we did an x0 that's kind of down here? So there's I have an exam question for it. Let's just try this one before we do exam question. So if I was to do here, so go up. No, it's not a very good diagram. Let me see. Yeah, I probably just need to go straight to exam question. No. 10B. Yeah, this one. Okay. So I'm just gonna make a new file so it's not so huge. Okay, so exam question. Start from B. And you can use your calculator if you like.
Okay. So sketch on the same axis y equals x and y equals x, y equals root 6x minus 1. I was about to ask in the actual exam, will I be able to use my graphical calculator, but that's not going to happen.
Yeah, snaking.
Zoom auto. Okay, so it's a graph, y equals x, and then a root graph, that starts at 0, then curves upwards.
Yeah, and I think it would kind of curve downwards, am I right?
Did I copy it wrong? No. It starts at 0, it goes up, but then it curves down.
Yeah, okay. Let's see. So, number of roots.
So there are 2.
Okay. And then, how do you do D?
So number right, there are 2. So D, use your diagram to explain why the iterative formula converges to a root of x. So explain why the iterative formula converges to a root when x0 equals 2. I'm not sure how to answer
that. You would just do a staircase cobweb, a staircase or cobweb diagram.
Okay.
So, let's say x is 2 here.
Yeah.
It's black. So you go up, hit the curve.
Mm-hmm.
So always hit the curve first. Hit the curve and then go across, hit the line.
Yep.
So it's our little robot doing it for us. And just keep repeating that. Hit the curve, line, and that's your whole answer.
Mm-hmm.
So that's actually the answer. Let me just... yeah. So you can see there, curve, line, and C diagram above. So that is the actual answer.
Okay. If you have a function,
Mhm.
I saw the diagram for the next question, but actually no, we'll cover it maybe once.
So they then give you a different function for the
Mm-hmm.
next one. So how would you do that one?
X squared n plus 1 over 6. And then so by sketching a diagram, explain why the iteration diverges when it's 0. So I would draw the graph first. So I use my calculator. So that's x squared plus 1 over 6. So it's kind of like a parabola.
Mm-hmm.
Touches at 0 and goes up again. And then y equals x obviously intercepts twice. Fascinating, actually. I never realized. Obviously they would, but they all meet at the same point.
Mm-hmm.
But 10 is past the point of intersection, and as we can see, the functions are increasing. Their second derivative is greater.
Mm-hmm.
Well, it's larger. So if you use the step method, it'll then reach until the number is too big.
Yes, and so you would do your thing, and like you said, because the second derivative, the rate of increase is increasing, the stairs are going to keep getting bigger. Your diagram is hopefully better than mine, and this is their whole answer.
Yeah.
So that's actually what their answer is.
What is the cobweb? Is it the same idea?
Similar idea. It just has a different outcome. I'll show you. So that's what it can look like. I'll give you a simpler cobweb. Yeah. So with this one, they give you x0, and let's use red. And so you go up. This is y equals x. Do we go across from there?
Mm-hmm.
No. Always hit the curve.
Sorry.
Always hit the curve first.
Okay.
So hit the curve, curve, line. And so this is graphically what your calculator is doing when you sub answer in. It is converting your previous y into your new x.
So when you do it before, when we had, the simple increasing and y equals x, do we always solve the robot to the right?
With the simple... the staircase one?
So with the staircase, does it always solve to the right?
No. This one's moving to the left. Is that what you mean?
Yeah. How do you know which way it's meant to solve?
It will always be... so go up from x0, hit the function, and then y equals x. And that swaps your previous y into your new x.
Mm-hmm.
And so in this case, it went from right to left.
Oh, so it always goes towards y equals x.
What do you mean?
So if it hits the line, it always then goes to y equals x. So it goes
So
up
it's
as a curve.
always function line, function line, function line.
And it doesn't matter if it's on the same side of the curve or the other side of the curve. It always goes there.
Uh,
Because like here in Cobweb, it goes across the curve, if you see what I mean.
oh, I see what you're
Whereas here
saying.
it stays inside.
Yeah. So in this case, it's because so this is a different type of cobweb, I suppose. You with the previous type, you passed through the line.
Mm.
So here you pass through the line in order to hit a curve.
Yeah.
In this type, you don't have to pass through the line first. So you
Mm.
just hit the curve, then the curve line.
Yeah, I see, I
That's the
see, I
only
see.
difference. But there are certain circumstances where it doesn't converge, and we saw one of those here. So when you're kind of inside, it will converge. In this case, it will diverge. It's
Mm-hmm.
outside, and it's the second derivative is increasing. Yeah. Any other questions about that stuff?
No, I think I finally understand it, yeah.
And yeah, it's just a visual way of showing what your calculator is doing. It's taking the previous y and subbing it in to be your new x. And what else was I going to say? Yeah, this is the only question in the book about it.
Sorry, I just...
Okay.
Okay.
This is the only question about it in the book, like exam question, and that's because it's a rare exam question that would ask you to draw a staircase or cobweb diagram.
Mm-hmm.
They mostly don't look like that. Anyway, let us resume. Let's
Okay.
see.
So I believe Rafson thingy is next.
You cheek dust man. Okay. Let me at least do some. You're like a moga. You're just like, so the next thing and the next. But what about this? Something going on in that school.
Is, yeah, we're still too hooked on the A levels, you know.
Let's see. So I just want to show you what the exam questions all look like, and they're all very, very similar. So
Okay.
this one, show that this equation. Yes, there's one little thing we have to do. How would you do question B for this one?
Question B, so f of x equals 3 plus x squared minus x cubed. And B is change of sign of f of x. Justify that alpha is 1.8. Is alpha the point of intersection?
Yeah,
The first
the
point.
root.
Yeah. So consider. Oh, and they give you. Oh wait, no. Do we use the interval from above? No, that's different.
That's different. Any idea how you can show this to 3 decimal places?
Verify that alpha is. Would we use the iterative kind of going through the calculator sort of thing?
So that's what everyone thinks, and they get 0 marks.
Uh-huh.
The way you have to do it, and so it seems like that would be enough, that you would just kind of, put in like 1.85 or something. Just keep pressing equals, and it'll go to some number that will round to that. In reality, you have to unround this one to its lower bound and its upper bound to 4 decimal places. What will those be?
To 4 decimal places.
Yeah.
So 1.86. The lower bound is 3.5. And then the upper bound is 1.86. 8654. No, 45.
Yeah, and it's a bound, so it's not including that one. So that's all I have to worry about. What would you do with those?
Would we? What I'd think is, give the iterative formula again with those bounds.
0 mark.
0 marks.
0 marks. What you would do is sub it in. So sub those in. Tell me what you get.
Oh, we just do it old-fashioned way.
Yeah, verify.
Ah. Okay, so if I do 3 plus 1.6835 squared minus 1.6835 cubed, 1.0628.
Okay.
Oh, I wrote the 6 and the 8 the wrong way around.
Yeah, it seemed like it was too big.
Yeah.
Also, my handwriting is atrocious.
1.382 times 10 to the minus root.
10 to the minus 3. So that's a number that's very close to 0. Okay, and positive. How about the other one?
And then the other one is 4.5 minus 5.3134 times 10 to the minus 3. So with this, what we're finding is that the root is in between these two bounds, basically.
How do you know?
Because there's a change in sign, and it's a continuous function between this interval.
Yeah.
How do we know if it's not a continuous between the interval?
So looking at the function, what are you not seeing?
1 over x.
Yeah, there's no fraction with x on the bottom, so you can't divide by 0.
Mm-hmm.
Sign change. Function is continuous. Therefore, alpha is equal to 1.86423 decimal places. Yeah, so we did above it and below it to 4 decimal places, like lower bound, upper bound, and so it definitely will round to 3 decimal places to this. And you could see that if we got the exact root is when the f of x is equal to 0.
Mm-hmm.
And so this is very close to 0, but it's positive. Very close to 0, but it's negative. And so, yeah. That's question. Let me just see something. Just want to make sure about that last thing. So that's numerical methods. Is it A, question 2? There is a change of sign, so there is a root alpha in the interval 1.8 to 1.9. No, that's part A. Yes, interval 1.8635, 1.8645. So the f of that is greater than 0. The f of that is less than 0. Change of sign in the interval. So alpha is 1.6423 decimal place. So alpha.
Mm-hmm.
Yep.
Okay.
Great. And so let me just. So that was that one. So that's how you verify. So you can see. How would you do part B for question 3?
Part B, for choose suitable interval, show that alpha is 1.441, so then you choose 1.405 and 1.4415, and then you just do it between those two boundaries. You sub it in.
Yes, and so what you can see is part A, show that there is a root in that interval, and then part B, verify that this is the root to 3 decimal places.
So it's the same sort of idea.
Yeah, and so you can see they used like e to the x, they used the square root, they used over x. There were some other little things, but those are kind of different. Find the coordinates of stationary points and stuff. So that's just differentiation and stuff. Okay, so staircase diagram, we saw that. That's what it visually looks like. Cobweb, this is what this one looks like. Yep. And then this, we saw that's divergent. Let me see. Show that this equation can be written like that. Yeah, fine. Exam questions. We did it. And then this one, show that this equation. What would you have to? How could you convert this one up here to look like this one? What's the main thing you have to do?
Show that. Oh, Um, so obviously you want to get x cubed on the left-hand side first.
Correct.
And then you divide by 3, and then then you cube root it.
Yes, and you'll be fine. How about this one?
Actually, question about just putting stuff in form. If it says, cube root px to the 4 plus q, if you have something that's, say, 3x to the 4 plus 2 over 5, is that still in the form?
I would change it to be p over 5. So it would be like, if it was 2x to the 4 over 5, I would write it, I would say p is 2/5.
Oh, I see.
And then do the same with q. If q was 3, then that's 3/5, something like that.
Yeah, I see. Okay.
So question 7, how would you go about doing A?
So show that the equation can be written in cos. So then we get. That's root. So what we do is we bring the 3 cos x squared to be the main thing.
Yep.
So then it becomes 2 minus x. We divide by 3, so that becomes 2 minus x over 3. Then we square root everything to get root.
Before that?
Oh yeah, because brackets. We arc cos and then.
Yes.
So trig comes after multiplication division, but before indices.
It could just work from the outside in.
Okay.
So cos is on the outside, x squared is on the inside. So just outer before inner. Yeah, work from the outside in. So if you see arc cos, make cos the subject and then arc cos both sides. Yeah. They wrote it as the power of a half. That's just the same as square root. So yeah, you have the idea for these. You can see there, show that this can be written as ln something. They just made e to the x the subject and then did ln to both sides. And so it's the same thing over and over again.
Yay, Newton-Raphson.
You and your Newton-Raphson. Okay, so Newton-Raphson is how you solve something with your calculator.
Sure.
And it kind of like takes a second to calculate it and then it comes up with an answer.
Yeah.
So the calculator uses the Newton-Raphson method, and so it's a good way because it just calculates pretty much everything. This is the formula: xn minus the function over the derivative of the function.
Xn plus 1 equals xn over f. So it's the xn minus the function over the derivative.
Yep.
I may need a bit of explaining.
And that's you're subbing in answer, so it'd be like answer minus f of answer over f dash of answer. Let's see the value of this one.
So this is used just finding roots, right?
Yeah, this is just for finding roots, but it won't get you an answer like an exact answer like ln x or something like ln 3 or e to the 7. It always gets you like the 3 or 4 decimal places. So it just
sure.
Thing. Okay, let us try this one.
Okay. F of x, f of x. Okay. X P A. Okay, so the equation f is root alpha in the interval 1 a alpha 1.9. Why x0 because P is not suitable to use as a first approximation when applying the Newton-Raphson method. I'm inclined to say because it's at the peak, but I don't know what that actually means. What would mean?
This we call a trough.
Trough, yeah, sorry.
What is the formula for Newton-Raphson?
Xn minus f of x1 over f dash xn.
And so, what is f dash of x at the point A?
0.
Yes, you'd be
So it
dividing by
comes
0.
up. So what does that mean?
You would be dividing by 0. And that's why you wouldn't use the bottom.
What does divided by 0 mean?
Can't do it. Undefined. How many zeros are in 1?
Oh, but what about 0 over 1? Is that just 0?
That's a 0.
Oh, okay, I see. So x over 0 is undefined. I get mixed up between the two.
That's alright.
Okay.
So try part B.
Part B. X equals 0. Oh, x0 equals 2. Use it twice to f of x. So we do 2 minus...
hold on.
Oh.
Possibly. I would do 2 and press equals.
Okay.
And then use answer.
Cool. So answer...
And I'm just going to do some crazy stuff, so you just do your own thing there.
Okay. And we're using the f of x above x cubed plus 2x squared, right?
To apply twice. Yep.
Okay. The derivative of that, okay. Oh, you're cheating.
Yep.
I get 28 over 15.
Me too. Oh.
When you do the d by dx thing, do you have to have a number input? So like x has to be defined as something.
Here's what I had to do. So we had answer minus.
At the end this is what x is.
F of answer. So like answer cubed plus 2 answer squared minus 5 answer minus 4. And so what goes on the bottom of the...
Underneath what the derivative?
Yeah.
3 answer squared plus 4 answer.
Yes. So f dash of x is 3x squared plus 4x. Something's missing.
Did I miss something? No? Oh, minus 5.
Yeah. So that's how I had to do this one. You don't be fancy like me. And did you get 2 answers for that one.
I only got one answer for that one. Oh, and click it again.
Mm-hmm.
I get the same.
That
Yeah, I
one.
get the same thing.
Okay. And
Wait.
then what is...
I don't know. It's not going through with it.
Say it again, sorry?
It's not going through with it. It's not giving me like the next answer.
That's okay. Did it give you the 1.8?
Oh yeah, it has. It has. Yeah,
So it
1.8.
was just calculating it, was it?
No, I clicked it and it wasn't. It
Okay.
was just being a bit odd.
Okay. Because, sometimes it goes blank because it's actually calculating.
Yeah.
Um,
Maybe it was doing that. I'm not sure. I didn't look at the symbol.
Part C.
Let's see. Considering the change of sign of f of x over an appropriate interval show that your answer to part B is accurate to 3 places. So we have 1.856 basically as our thing.
Mm-hmm.
So then should we do, one up, one down, kind of a boundaries?
Yeah.
So our boundary is 1.85. They wanted 3 decimal places, so we need to do 4, so 8558. So our upper bound is 1.856. 5. No. Okay, we have 1.856.
Mm-hmm.
1.856. Our upper bound is 1.8565, and our lower bound is 1.8555. There we go.
Mm-hmm.
So then what we do is we substitute these into f of x.
Yeah. And what would you get?
And then we get one tiny positive, one tiny negative, and then we can just say that our answer is appropriate.
And go on, what are the exact stuff you have to say?
There's a change in sign, then in this interval where the function is continuous, therefore there is a root.
Sounds good to me. Let's see. Yes, so you know how we were doing that stuff before, where you make x the subject, make it x, square root both sides or cube root both sides. This is a method that will always work. So just go.
Okay.
So just go with initial value minus function of initial value over derivative of function with initial value, and just keep this in equals. And so in general, this method will always work.
So it just makes iterative, what we were doing before, useless.
Not useless, Gregoire. But this is a general thing. So before, you don't. So this is a cubic. So you don't have to use arcsine or any of that stuff. I suppose what's kind of different about this is it's very dependent on the initial value.
Sure.
Will get you different roots, whereas with the other one you could use a different, you could use the square root to get one root, the cube root to get a different root, that type of thing. With this is dependent on the initial value. Very small number that's less than 0, very small number that's that should say greater than 0, that's misprint. Sign change in the interval, therefore x is accurate to 3 decimal places. Exam questions. Use differentiation to find f dash of x, and the root lies in that interval. Apply the Newton-Raphson method. You think you'd be okay with that?
Which question were we looking at? 3.
I was just looking at question 2, part B.
Oh. They could do this approximation to apply process to fx. So then we just use 0.4 as the answer. Maybe just use the equation.
What is the equation?
It is approximation minus approximation in the function over the derivative of the approximation in the function.
Yes. And so, so minus 0.4, it'll be plus, the numerator will be answer squared minus 4 over answer plus 6 times answer minus 10. And then the denominator will be the derivative of that function with answer
Yeah.
subbed in. So it looks like they use different values, like here e to the minus x. Explain why. So part A. What is part A for this one?
But A, explain why x0 equals q is not suitable to use. Explanation. Where is x0 equals q? Oh, it's a stationary point. So yeah, it's when the derivative of a function is 0, so you can't use it.
Why not?
Because 1 over 0 is undefined.
Yeah, can't divide by 0.
Is it also? Could you also say it's not continuous?
Looks continuous to me.
Fair enough.
There's no break in the line, and also it could be discontinuous at a different part. Yeah, it is. It's discontinuous when x is 0, but I think they're talking about this interval, like bigger than 0 and less than there. I can see 2 roots. Yeah, so you're right. It is discontinuous. That's probably why they cut out the left side. They used to really be into their continuity stuff. Now, not so much. Newton-Raphson, fine. Show that there's a root there. Differentiate, and then Newton-Raphson. Show that the curve has roots in these intervals. Okay.
That we can't use Newton-Raphson for that one, can we?
For this one up here?
For intervals.
No, they're just kind of mixing them in now. So you would just sub in 0.6 and 0.7 and say like sign changes, function is continuous in the interval, therefore root.
Okay.
Same with this one, same with this one.
Yeah.
This one divide by 0, and then this one unround it. Let's see, has a root in there, f dash of x, so yeah, there you go. Newton-Raphson, what do you give yourself?
I think a little bit of practice just to familiarise myself with it.
Yeah, and it looks like there's modelling at the end. So most chapters have some kind of modelling at the end, and that just means applying it to the real world.
Right. Okay.
If you like, we can do that next time, or we can do something different. It's up to you.
At the moment, it's up in the blue.
Yeah.
I'd say just keep it for now, but chances are I'll probably find something else to work on.
Okay.
Yeah.
Any
If you have any resources, like